Okay guys, in preparation for this upcoming test on projectile motion, to help you guys kind of get prepped, I decided I would do a few practice problems. So I'm going to make up 4 different problems and do them in real time. I'm sort of making them up and going over them right here in real time, so bear with me. Basically, there are 4 different types of problems that we've worked on this chapter, and I'd like to do an example of each. So the first type of problem, the simplest problem, so this will be the first type, are horizontally launched projectiles. So you could definitely see a problem like this on the test. I consider these to be easy problems. Could even show up in a multiple choice question. It should be relatively quick, provided you're pretty competent. So let's imagine we have like a table here, and maybe the table has a height of, I don't know, let's say it's 1.4 meters. So this is the height of the table, 1.4 meters. And maybe I've got some kind of a ball here that's going to roll off of the table, and it's going to roll off the table with a horizontal velocity. So this is not up or down at any angle, just straight out horizontally at, let's say, 5 meters per second. And we know, of course, that the ball is going to enter projectile motion and do the parabola thing and land over here somewhere. And the question is, what's the range of the ball, right? And by range, whenever we see this range, right, this should immediately clue us in that we're looking for delta x. That's this distance right here. We'd like to know that delta x. And these are the simplest types of problems because I don't have to worry about fiddling with my initial velocity. This is Vx. The initial velocity is entirely in the x direction, so this is an x velocity. So when I want to calculate delta x, I use my delta x equation, v sub x times t. And this is very simple because I know v sub x. I don't have to do any work to find it. This is 5 times t. So to figure out delta x now, if I can determine the t value here, then I'm home free. So then I say, okay, well, what in this problem determines the time? And that, of course, is the delta y value, which, careful and recognize that the ball is going down, so I need to make my delta y negative. So I'm going to say negative 1.4, it's my delta y, equals v initial y times t minus 4.9 t squared. That's g over 2 is 4.9. I make it negative because g is negative. And now we also remember another reason these problems are easier. The v initial y is 0, which means this whole term vanishes. Right? The ball rolls off with a velocity that's horizontal, so there's no y component. And so now I can say negative 1.4 equals negative 4.9 t squared. So I'm going to say, give myself a little more room here. I'm going to say t is the square root of negative 1.4 divided by negative 4.9. Take out my calculator here, my handy calculator. Hopefully you can see this. And I'm going to say, turn her on. Is that not working? Oh, there we go. Square root of negative 4.9. Of course, the negatives are going to go away, but negative 1.4 divided by negative 4.9. And I end up with a time value of, what is this point? Let's call it 0.53 seconds. This time here, this gets plugged in up here, and I end up with a delta x now. Final step, these are my steps. So this is step 1, step 2, and then my third step over here. I'm going to say delta x then is 5 times 0.53, which is, get back to my calculator, so multiply that by 5. And I get 2.67 meters. Okay, done. Final answer. There it is. Again, I'm assuming that this is an easy problem. Okay, so this is easy problem. So again, this is something you might see potentially in a multiple choice question. This should only take you, if you know what you're doing, a minute or two to solve. It shouldn't take a very long time. Let's move on to a harder problem. The next level of difficulty problem was a problem where we had a projectile launched at an angle but over level ground. So here's flat ground here. This is maybe it's some field, and we have some object, maybe it's a ball here, that's going to get kicked upward at an angle. And we know the velocity. Let's say that this initial velocity v is, I don't know, let's say it's 15 meters per second. And let's say that this angle right here is, I don't know, let's call it 25 degrees. So that's 25 degrees, 15 meters per second. And maybe I'd like to know two things. Maybe I want to know the range. So it's supposed to be an A, believe it or not. So A, what is the range? And maybe I'm going to ask you this time too to find the maximum height as well. Maximum height. So those are two things that we'd like to find. All right, well, range, let's do part A. This is very similar to the last problem we did. We're going to say V sub x, or sorry, we're going to say delta x, that's the range, equals V sub x times t. Right, so what's, just so we understand what's going on, right, the ball is going to do its old parabola thing again and land over here somewhere. So here's our delta x. What makes this problem slightly trickier is that not only do I not know t, but I don't know vx either, right? This velocity is the full speed at the angle, right? I need to know right now, I need to figure out what is the x component of this velocity. What is vx? And hopefully we see immediately that this is 15 cosine 25. So maybe I'll just go ahead and calculate that right away. 15 cosine 25. 14 point, let's call it 14.9. So now I can say delta x is 14.9 t. So this isn't a lot harder. There's just this one extra step. I needed to do a little bit of work to find the initial x velocity. So now I've got to find t. What do I use to find t? As I did before, I'm going to use my delta y, and I ask myself, what is delta y in this case? Well, the ball starts on the ground and ends on the ground, so the delta y is 0. So I say 0 equals, what is my initial y velocity? Well, I have to find that as well. It's this initial y. V initial in the y direction is 15 sine 25. So let's go ahead and find that. 15 sine 25. Ooh, uh-oh, I made a mistake. Wrong mode. I should have recognized that earlier. I've got to recalculate. 15, I got to recalculate the cosine. 15 cosine 25 is 13.6, and 15 sine 25 is 6 point, let's call it 6.3. So 6.3 and 13.6. So this is 13.6. And this is 6.3. 13.6, did I do that right? Yeah, 13.6, and this is 6.3 t minus 4.9 t squared. How do I solve this? Well, since there's a 0 over here, I don't have to deal with the quadratic. I can just factor out a t, and I end up with 0 equals t times 6.3 minus 4.9 t. I get two roots, 0, which is, that's just telling me the ball's on the ground before it was in motion, which I knew. That's not the root I'm looking for. The root I am looking for, if I set this whole thing equal to 0 and solve, right, I'm going to get a t value of negative 6.3 divided by negative 4.9. Now, this is the root I don't care about. It's this root that I do care about. So let's figure out what that is. Back to the calculator. I know the negatives go away, so I'm just going to say 6.3 divided by 4.9. So that's 1.28 equals 1.28 seconds. Plug that in over here. 13.6 times 1.28. That's, so I have to take this now and multiply by 13.6. Oh shoot. Times the answer that I got there. And that gives me 16.7 meters. Good. And that's the answer for part A. So we found the range, we've gotten that. Now we want to know the maximum height. So let's think about it. The very, very tip top, what do we know? Hopefully we remember that way up here at the very, very tip top, the y velocity at that point is 0. And so to find that maximum height, the way I recommend doing this is to use, I'm going to try to get some more space over here. This is part B now. To use one of our other kinematic equations, which is v final squared equals v initial squared plus 2 times a times delta x. This is one of our kinematic equations. This applies anytime there's uniform acceleration. And since there's uniform acceleration in the y direction, I can use this equation. I'm just going to repurpose it slightly. I'm going to say v final y equals v initial y times 2. A now, what is A? A is g, right? A is negative 9.8. And this delta x I'm now going to call delta y. Maybe I should go ahead and erase that so you can understand what I'm doing here. I'm calling this delta y. Okay, well, what's v final y? Well, I'm talking about the very tip-top point. I'm calling this point where this is 0. So I say 0 equals the initial y velocity, which was 6.3 squared, minus 2, I'm making g negative, so this turns into a negative, minus 2 times 9.8 times delta y. And now I can solve for delta y. Delta y is negative 6.3 squared divided by 2 times negative 9.8, that's negative 19.6. Calculate. The negatives go away, of course. I end up with 6.3 squared divided by 19.6. That gives me about 2 meters. So 2 meters. That is the maximum height. You might say, well, that sounds awfully low, but this ball was kicked at a pretty shallow angle, 25 degrees. It didn't go very high. Okay. 2 problems down. 2 to go. All right. Number 3. The third, this is a slightly trickier problem, is when you have a projectile launched at an angle, but delta y isn't 0. So, let's try a problem like this. Maybe I'll do this. We'll make it easy on ourselves. Here, we're gonna have the same soccer ball as before, kicked, but rather than being kicked off of level ground, maybe it's kicked off of this little drop off. We've got a little hill here, maybe, and this is, let's say that this is 20 meters high. Pretty significant little drop off. And we have that same ball Here's that ball that we kicked last problem. So we're kicking it once again, 15 meters per second. And we're kicking it at this angle of 25 degrees. So now it's going to do this thing, right? It's going to go up and then down. Okay. Let's see, what do I want to find? Let's find the range. So here are our questions. We want the range, and we want to know, what do we want to know? Oh, how about the final speed of the ball when it lands? The final, or let's call it the landing speed. The speed it hits the ground with. Landing speed. All right, part A. Here we go. Very similar to before, I'm going to use my delta x equations and my delta y equations. So it's going to be very similar. There's just going to be one additional step of algebra. So let's remember what we did last time. We already know from last time that my Vx is, what is it, 13.6? Is that what we found? Yeah, 13.6. And my V initial y is, what did we have up here? 6.3. Okay, so now if I want to know my delta x, I'm going to say delta x is Vx 13.6 times t. And if I can find t, I'm home free. How do I find t? From the delta y. So how do I use the delta y equation? This is going to be a little trickier because my delta y is not 0. This is, my delta y is negative 20. So now I say negative 20 equals 6.3 t minus 4.9 t squared. There's not a 0 over here, so I can't go ahead and factor out a t. That doesn't work. What I'm going to do is I'm going to move everything over to the left-hand side, and I'm going to say 4.9 t squared minus 6.3 t minus 20 equals 0. This is a quadratic equation. I recommend that you solve this by graphing. So I'm going to graph this thing. I'm going to say 4.9 x squared minus 6.3 x minus 20. I'm going to graph that. And I see there's a 0. There are two zeros, in fact. One of them is negative. I'm not interested in that 0 right here. But that one's positive. I'd like to calculate that. So I want the calculate function, so I hit second trace to get the calculate. I want the 0, so I hit 2. It asks me for the left bound. So what I've got to do now is keep moving the cursor over until I'm just left of the 0 point. Keep moving. There it is. I want to be just left of the 0 point. So that's just left of the 0 point. I hit enter. Now it wants the right bound. I want to move just right of the 0 point. There we go. Enter. Hit enter one more time. And here it is. Here's my 0 that I want. It's 2.76 seconds. So I say t equals 2.76 seconds. That's what I'm interested in. That's the time I want, which I can now plug in right here. And I end up with a delta x of 13.6 times 2.76, which is, back to the calculator, 13.6 times 2.76, 37.5. 37.5 meters, which, by the way, is way farther than we got up here, right? Here we only got 16.7 meters. Now we get 37. Why so much more? Well, since we kicked the ball off this cliff, the ball's in the air for a hell of a lot longer, so it travels a greater distance. All right, how about the second question? This is a nasty one. What is the landing speed? So it lands here, and we want to know the speed with which it lands. So first of all, let's recognize that when it lands, it has two kinds of velocity. It has a horizontal velocity, right? So it's got a a Vx. And I'm going to clear up some space here. Erase some of this. And it's also going to have a Vy, right? It's going to have an x and a y velocity. So let's go ahead and see that we've got a Vx and we're going to have a Vy. What is the speed? Well, the speed is going to be the vector sum of the two. So to find the final speed, I need to calculate this hypotenuse, right? This is what I'm looking for. This is my final speed. All right, well, can I find these Vx and Vy? Sure, Vx I know. It doesn't change, right? This is constant. So the x velocity is just 13.6. The y velocity I have to calculate. How do I find this? Well, if I remember, we have a kinematic equation that looks like this. An old kinematic equation that said V final is V initial plus AT. I can apply this in the y direction because there's uniform acceleration in the y direction. So this Vy is going to be my initial y velocity, V initial y. What's my V initial y? Well, that was 6.3. Plus a, well, a is negative 9.8, so I'm going to say minus 9.8 times t. What's t? Well, it's 2.76. So let's use the calculator again. 6.3 minus 9.8 times 2.76, and I get negative 20.7. Why negative? Because the ball is going down when it lands, so it makes sense that this would be negative. So this is negative 20.7. All right, well, what's the final speed then? B, so I'm doing part B now. Move down here for part B. The final speed is going to be the vector sum of this and this, right? So it's going to be the square root of 13.6 squared plus negative 20.7 squared. So that's going to be, let's do this, get my calculator back, square root of 13.6 squared plus negative 20.7 squared. Oop, I screwed something up there, didn't I? Negative 20.7 squared. And I end up with, oh, what did I do? Huh. What have I done? Doesn't seem to want that. This guy there, does it? What happens if I hit enter now? Oh, it still doesn't like it. Oh, I know what I screwed up my parentheses. So what my calculator has done is it's read this as negative 1 times 20.7 squared. So what do I have to do? I have to put, I screwed up my parentheses. I need to put my parenthesis here. Squared, close parentheses. Now it'll like my answer. I had to tell the calculator to square the whole negative number, right? So I get 24.8. So this is 24.8 meters per second. Okay, so that's the speed with which the ball lands. Great, so far we've used I think we've used just about every equation that we need. Let's try the hardest type of problem, so the last type of problem. These are problems where you don't have the initial velocity. So let's say I'm going to do a slightly easier version of this type of problem. We did a harder one in class, or a couple harder ones in class, but I'm going to do a problem where we don't know the initial velocity, but we do know that the ground is level. Because I want to remember, and there's one equation that we did use that I haven't used yet. Here's a ball, and it's kicked now at an angle of 40 degrees. We don't know how fast it's kicked, but we do know that it's going to go a delta x, it's going to travel a horizontal distance of, let's say, 28 meters. And what do I want to know? I want to know, I'm going to ask two questions. I'm going to ask again for the, I'm going to ask for V initial. What is this V initial that it's launched with? And what is, let's see, what do I want to ask? What is the velocity? Or no, how about this? Is it at t equals 1 second, is it going up or down? That's very messy. I hope you can read that. Is it going? I think I have an extra letter in there. At 1 second, is the ball going up or down? I don't know how well this is going to work because I'm just making this up. Going up or down. But I'll show you the method anyway. So part A, what is the initial velocity? Here's where if you go ahead and use your delta x and delta y, it becomes tricky because you say delta x is 28. So I'm going to say 28 equals Vx times t. And here's where you say to yourself, I don't know Vx, right? I know that this is some velocity v, but I don't know Vx. I don't even know v. And then you say, all right, well, what does the delta y look like? Well, delta y is 0. 0 is the initial y times t minus 4.9 t squared. And here you say, uh-oh, I don't know v initial y and t, and I've got 3 unknowns. This is an unknown, right? We call that unknown 1. T is an unknown that we can call unknown 2 if we wanted. And then this is a third unknown, right? This t is the same as that t. This t is the same as that t. I can't solve an equation of when I have 2 equations with 3 unknowns. Really quickly, I'm not going to do the problem this way because there is an easier way. But you might remember that you can express Vx and v initial y in terms of v. I can call Vx v, I don't know what v is, I'm just going to call it v, cos 40. And I can call v initial y v sine 40. And then I can work my substitution. So if I put in now v cos 40 in right here, and v sine 40 in right here, then I end up with an equation, 2 equations with 2 unknowns, which I can solve by substitution. I'm not going to do it that way, though. I'm not going to finish it off that way. But you might want to review this. We did problems in class like this. You might want to review this. I'm going to point out that in this particular problem, I can do it a much easier way. How? Because I know that the delta y is 0. And since the delta y is 0, I can use another equation, the range equation. If you remember the range equation says the range is the initial velocity v squared times the sine of 2 theta over g. You don't need this equation. You can solve this problem in this method. If you happen to memorize or know this equation off the top of your head, it makes this problem a lot easier because now I can solve for v. That v, the v initial, is this guy right here. And I know the range, I know g, and I know theta. So I can go ahead and solve for v. Right? I'm going to say, maybe give myself a little more room here. I'm going to say 28 equals v squared sine, theta was 40, so 2 theta is 80 over 9.8. Okay, so now what am I going to do? I'm going to solve for v, and I'm going to say v, well, let's say v squared is 28 times 9.8 divided by, so just multiply both sides by 9.8, divided by the sine of 80. So if that's what v squared is, then v is just going to be the square root of this thing, right? So here we go. What is V? Calculator out. Square root of 28 times 9.8 divided by the cosine, or sorry, sine of 80. And I end up with 16.7. So here we go. Oh, what am I doing here? 16.7 meters per second. That's a lot easier than having to do the substitution. So if you happen to remember this range equation, it does, in certain circumstances, make your life a hell of a lot easier. Okay, part B. Well, at t equals 1 second, is it going up or down? Well, how do I know if it's going up or down? Well, I know if it's going up or down by the y velocity. So for part B, I'll do part B down here. Part B. If the velocity in the y direction is positive, then it's going up. If velocity in the y direction at 1 second, if it's negative, then I know it's going down. So what can I do? Well, I can use one of my kinematic equations. I'm going to say V final y equals V initial y plus gt, where I remember that g is negative. So usually I'm just going to go ahead and remember, since g is negative, I'm just going to go ahead and call this negative. All right, well, let's find V final y. V initial y, I can find that now, right? Up here, I know it's V sine 40. And I know V. V is 16.7. So V initial y, this is 16.7 sine 40 minus 9.8. And what was my time? 1 second. So here we go. Might be obvious what this is going to be. But, so I'm going to take the answer that I got, 16.9, times the sine of 40. So that's the initial velocity minus 9.8 times 1, which is just 9.8. And I end up with 0.93 meters per second. So it's positive 0.93 meters per second. So actually, it worked out pretty well. This is pretty close to the top, but since it's positive, it's still going up. So it's still rising at that point. Okay, guys, 4 problems, an exhaustive review, or not exhaustive, but an exhausting, for me, review of 4 different types of problems you could see on the quiz. Hope that helps.